Dear students, this is Dr. Anusia, Assistant Professor of Mathematics. In this video, I am going to explain the diagonalization process of a matrix by orthogonal transformation. Now, uh, let's see what is orthogonal transformation. If we have a square matrix A, then that matrix A is said to be orthogonally diagonalizable if there exists an orthogonal matrix N such that N inverse AN equal to D implies N transpose AN equal to D. Here we remember that uh, the the definition of orthogonal matrix. Suppose n is orthogonal matrix, then it should satisfy the condition n transpose n equal to n into n transpose equal to I. This transformation that is which transforms A into D is called orthogonal transformation or orthogonal reduction. Let's see an important theorem. If we have a symmetric matrix A of order n and x1, x2 up to xn be eigenvectors of A, and these eigenvectors are pairwise orthogonal. Remember what is pairwise orthogonal? If we take any two of these eigenvectors, suppose I take x2 and x4, then x2 x4 transpose equal to 0. This is called pairwise orthogonal. If next I take a matrix formed with normalized eigenvectors as n or as columns, then n is orthogonal matrix such that n inverse an equal to D implies n transpose an equal to D. This n is called normalized model matrix of A or normal model matrix of A. Diagonalization of a matrix is the process of finding a diagonal matrix that is similar to a given square matrix. This method is only applicable for symmetric matrix. Now let's see the working rule for the orthogonal reduction of n cross n symmetric matrix. The first step is we have to find eigenvalues lambda 1, lambda 2 up to lambda n for the given matrix. The second step is we need to find eigenvectors, corresponding eigenvectors for each eigenvalue lambda 1, lambda 2, lambda n, which are pairwise orthogonal. The step 3 is we form the normalized model matrix N with normalized eigenvectors as columns. Next, we find N transpose and AN. The final step is we compute N transpose AN equal to D, which is the required diagonal matrix. We are going to solve the problem. Diagonalize the matrix A equal to 3, 1, 1, 1, 3, minus 1, 1, minus 1, 3 by means of an orthogonal transformation. The solution, the first we need to verify whether the matrix is symmetric or not symmetric. We are going to solve the problem diagonalize the matrix A by means of an orthogonal transformation. So first we need to check whether the given matrix is symmetric or not symmetric. Look at the matrix A, 3, 1, 1. The first row is equal to the first column and the second row is equal to second column. The third row 1, minus 1, 3 is equal to the third column 1, minus 1, 3. So the given now we verified the given matrix is symmetric. So the first step we have to find the eigenvalues of this matrix A. We know the before that we have to find characteristic equation of A. We know the formula lambda 3 minus s1 lambda square plus s2 lambda minus s3 equal to 0. First we have to find s1, which is equal to sum of the main diagonal elements. Next we need to find s2, then s3 is the determinant of the matrix, which is equal to 16. Now we find all the three things s1, s2, s3 we need to substitute these three things into the formula. We get the characteristic equation lambda cube minus lambda 9 lambda square plus 24 lambda minus 16 equal to 0. Now we need to find the roots of this equation, which is called eigenvalues. First, we try with lambda equal to 0, but it doesn't satisfy this equation. So next we move to lambda equal to 1. But lambda equal to 1 satisfies this equation. So we say that lambda equal to 1 is a root. Next we need to find other roots, other two roots by using synthetic method. Next, by using synthetic method, we find the roots lambda equal to 4 and 4. So these three roots 1, 4, 4 are the eigenvalues of this matrix. The next step is to find eigenvectors. Suppose if we take x equal to x1, x2, x3 is an eigenvector corresponding to the eigenvalue lambda. We need to find the equation A minus lambda I into x equal to 0. Here A is the given matrix and we keep it lambda with as it is, and I is the identity matrix, and capital X is the eigenvector x1, x2, x3. We substituting all the things, and by simplifying we get a system of equation with three variables x1, x2, x3. So the first case is we find eigenvector corresponding to the eigenvalue lambda equal to 1. By substituting lambda equal to 1 in the system of linear equation, we get 2x1 plus x2 equal plus x3 equal to 0, x1 plus 2x2 minus x3 equal to 0, x1 minus x2 plus 2x3 equal to 0. uh, we solve by solving these three equations. We get x1 equal to minus 1, x2 equal to 1, x3 equal to 1. So the eigenvector corresponding lambda equal to 1 is minus 1, 1, 1. Case 2 is we have to find the eigenvector corresponding to lambda equal to 4. So if we substitute lambda equal to 4, we get the three equations x1 minus x2 equal to x3 equal to 0. The second equation is also x1 minus x2 minus x3 equal to 0. The third equation is also x1 minus x2 minus x3 equal to 0. Three equations are equal to 0 or same. So now we have only one equation x1 minus x2 minus x3 equal to 0. So we have infinite number of solution. So we put x3 equal to 0. Then what we get is x1 equal to x2. So if we put x1 equal to 1, then we get x2 is also equal to 1. So the eigenvector is 1, 1, 0. Now we have to find the eigenvector x3. Suppose we let x3 equal to a, b, c, and which is orthogonal to x2. Then a plus b equal to 0. How can we find this as x2 transport into x3 equal to 0? By solving this, we get a plus b equal to 0. From this, we get b equal to minus a. Also, x3 should satisfy a minus b minus c equal to 0. Here, if we take a equal to 1, we get b equal to minus 1 and c equal to 2. So we found x3 equal to 1 minus 1, 2. So the eigenvalues are lambda equal to 1, 4 and 4. And the corresponding eigenvectors are x1 equal to minus 1, 1, 1, x2 equal to 1, 1, 0, x3 equal to 1, minus 1, 2. So the normalized eigenvectors are minus 1 by root 3, 1 by root 3, 1 by root 3 corresponding to x1. How will you find this normalized vector, eigenvector? First, we we divide each element in the x1, that is minus 1 1 1 by square root of sum of the squares of this element, that is root of minus 1 square plus 1 square plus 1 square. Similarly for x2, square root of 1 square plus 1 square, that is root 2. We divide all these elements by root 2. Similarly for x3, we divide 1 minus 1 2 by square root of 1 square plus minus 1 square plus 2 square. Okay. In this way we can find normalized eigenvectors. So the normalized matrix N is the combining all these eigenvectors into a single matrix is called normalized matrix. Next we find n transpose, that is transpose of the matrix n. Next we multiply n by a. Next we have to find n transpose an. Then we get the diagonal matrix 1 0 0 0 4 0 0 0 4, which is the required matrix. Diagonalization is useful because it simplifies computations involving the matrix, especially when raising it to integer powers. Thank you.